Hello students, in this video we are going to study about a spring. So basically there are three topics which we have to study in this video. So the very first thing that we have to study is the elastic force of a spring is a conservative force. So first thing we have to prove or study is that the elastic force that we have represented by Fs of a spring is a conservative force. This is the first thing that we have to study. After that, we will find the expression for the potential energy of an elastic stretched spring. So after proving this, we will find the expression for potential energy of an elastic stretched spring. And the third thing that we have to study is conservation of energy in elastic spring. Conservation of energy in elastic spring. These three topics we have to cover in this video. So first we are starting with the first one, that is the elastic force that is acting is a conservative force. This we have to prove. So for that we have considered an elastic spring here. This is of negligible small mass with its one end attached to a rigid support. This is a rigid support, and this elastic spring has its one end attached to this rigid support, and the other end of this spring is attached to a block of mass m. So this is a block of mass m we have assumed here, and the other end of the spring is attached to this block, and this block is sliding over a smooth horizontal surface. Since the surface is smooth horizontal, so we don't have to care about the friction. There is no friction, so the surface we have here is smooth and horizontal. Now the equilibrium position of this block we have considered is at x is equal to 0. So this is the equilibrium position. After that, when we stretch the spring or compressed the spring by pulling or pushing the block, a spring force Fs act there, and it always act towards the equilibrium position. So if we are stretching it, the Fs will act towards the equilibrium position, means x is equal to 0 like this. If we are stretching it towards right, then Fs will act towards left. Similarly, if we are pushing it towards left, or if we are compressing the spring force Fs will act towards the equilibrium position, that is towards right. So the direction of Fs is fixed. It always acts towards the equilibrium position that we have considered, this x is equal to 0 and represented by this dotted line. So this is how our system is working. Now according to Hooke's law, this spring force should be proportional to the displacement of the block from the equilibrium position. So that displacement is denoted by x in both cases, in stretching and in compression. So according to Hooke's law, this spring force that is acting towards equilibrium position in both cases is directly proportional to the displacement of the block from equilibrium position, that is Fs is proportional to x. Or if we remove this proportionality sign, then we have to insert a proportionality constant, that is kx. Now we have to put negative here because the sign negative represent the direction of force, this is spring force, and the displacement are opposite to each other. So if Fs is negative, x is positive. If Fs is positive, x is negative. So the significance of negative sign is that Fs acts in the opposite direction of x, and here k is a proportionality constant, and here it is known as spring constant, and its SI units can be given as Newton per meter, because k is equal to F upon x, so its unit will be Newton per meter. Now since this force is acting on the block, so the work done by the spring force for the small extension dx, if there is a small extension dx, then work done by this spring force for the small extension dx. Since the displacement we are considering, the extension we are considering is small, so work done will also be small, so we are denoting it by dw. So dws, because it is because of the spring force, is equal to fs dx, and we know that fs is equal to minus kx, so we are going to apply this value here. It will be minus kx dx. So this is the work done by the spring force for the small displacement dx. Now if the block is moved from some initial position xi to the final position xf, that means the displacement is xf minus xi, or initially it was at xi and final position is at xf. That means to find the total work done, we have to integrate this within the limits of xi to xf. So work done by the spring force means total work done during this motion, work done by the spring force, this ws is equal to integral of dws, and this integral we have to done in the limits of xi to xf. So it will be minus kx dx xi to xf, and when we solve it we get minus k constant, it will come out of the integral, and integral of x dx is x square upon 2 with limits xi upon xi and xf. So we have to apply limit, that is upper limit minus lower limit. When we apply this we get ws is equal to half k xf square minus half k xi square, but there is a negative sign outside it, so the final answer we get is ws is equal to half k xi square minus half k xf square. This is the work done. Now if the block is pulled from xi and allowed to return to xi, means if we pull the block from xi and it again allowed to go back to the position xi, that means आपका जो motion होगा it's like xi to xf then xf to xi. So the integral limit then in that case will be from xi to xi. The integral limit will be from xi to xi. So in that case work done will be minus kx dx xi to xi. So if we solve it we get minus k x square upon 2 xi. Now this is also xi to xi, and when we put these values we get the answer 0. So this shows that the spring force is position dependent. First thing, it shows that the spring force fs we have is position dependent. Second thing, the work done by the spring force depends on initial and final position and it follow Hooke's law. The third thing, the work done by the spring force during a cyclic motion. If there is a cyclic motion, means particle starts from this position xi and return back to its original position. In that case, in the cyclic process, this work done will be 0. So if we conclude all these points, then we can say that spring force is a conservative force, because conservative force are those which are path independent. Those work done will be path independent, and in case of cyclic motion the work done will be 0 under conservative force. So the conclusions we have, first conclusion we have is spring force, that is fs, is position dependent as it follows Hooke's law. Second thing, the work done by the spring force, this work done ws, depends on initial and final position, not on the path taken. Third thing, work done during a cyclic process is equal to 0. So all these points combinedly shows that the spring force is a conservative force. So that's how we prove that the spring force is a conservative force. Now after this, the second thing we have to find is potential energy of the spring. So if we want to pull the block outwards with a slow constant speed, we need a external force F which is equal to Fs has to be applied there. So if we want to pull the block, for that we need an external force F. Okay, so we need an external force to pull the block, let it be F, and it should be equal to the spring force. Only then we can pull that block outwards with a slow constant speed. Now the work done by the external force will be equal to the increase in potential of the spring, potential energy of that spring. So the work done that is done by this external force, which is equal to Fs, should be equal to the increase in potential energy of the spring. So this force, this external force, do some work. So the work done by the external force, that is capital F, will be equal to the increase in potential energy of spring. So we can write that the change or the increase in potential energy of the spring, that is delta U, is equal to W. This is the work done because of the force F, which is equal to the force Fs, and this work done that is done by Fs, we have already know that. So it is half k xf square minus half k xi square. Now if we take potential energy of the spring to be 0 when the block is in equilibrium, so initial point that we have taken when the block is in equilibrium, in that case we can take u at xi is equal to 0. This we are considering that at the point of equilibrium the potential energy is 0. Then the potential energy of a spring for an extension x, potential energy for a spring for an extension x means if the final position is x, then we can write the final potential energy as ux. Okay, so here from this equation delta u can be written as uxf minus uxi, and it is equal to half k xf square minus half k xi square. Now we are going to substitute these values in this equation. So it will be ux minus 0 is equal to half kx square minus 0 because xi is equal to 0. So we get the potential energy for the extension x is equal to half kx square. So this is the required potential energy of the spring for some extension x, and it is given as ux is equal to half kx square. Now the third thing that we have to study is the conservation of energy in an elastic spring. To understand this, we assume that the equilibrium position of our spring is this, x is equal to 0. We stretch it to some position x here and then release, and after that when we release it, it comes back to equilibrium position at x is equal to 0. And during this motion, the potential energy that we have at the extreme location here will convert into kinetic energy till this point, and at intermediate position, means at this position, the energy is partly kinetic, partly potential, and at that point the velocity of the body is maximum. At this point, at the intermediate position, the velocity of the body is maximum, and because of the inertia of motion, the body overshoots this position and start moving in this direction to a position x again. And at this point again, at this extreme position, the velocity becomes 0, and since the velocity becomes 0, it stops, and then the potential energy of the body again starts to convert into kinetic energy, and body starts moving towards the equilibrium position. So this is how that elastic spring show motion. Now we have two kinds of position. First is extreme position, means these are the two extreme position, and this is intermediate position. To prove the conservation of energy, we have to show that whether it is extreme position or it is intermediate position, the total energy of that stretched spring is same, then we can say that there is a conservation of energy exists in this system. So we are going to find the total energy in all these cases separately. First, let's talk about the extreme position. So at extreme positions, so we assume that the extreme positions that we are getting is at x is equal to xm. At these positions, if we stretch the spring to the distance xm, the velocity at these points is equal to 0. Since we are talking about both extreme positions, so we have to take plus and minus. If this is plus, this is minus. So at extreme positions, xm will denote the maximum distance to which we stretch the spring. So that's why it is the extreme position, and plus and minus because it is happening on both sides. We are stretching here and it get compressed on the other side to a distance xm also. At these extreme positions, the velocity of the spring is 0. So kinetic energy for these cases is half mv square. This is equal to 0. There is no kinetic energy, and the potential energy is equal to, we just derived the formula that potential energy of the spring is half kx square. So in this case, potential energy is equal to half kxm square because x is equal to xm. So this is the maximum value. This is the maximum value of potential energy we get, and that's why total energy is equal to 0 plus half k xm square and is equal to half k xm square. So this is the total energy of the system. Now let's talk about intermediate positions. Second thing is at intermediate positions means the positions that are between x is equal to 0 to x is equal to xm and x is equal to 0 to x is equal to minus xm. Means basically intermediate position means minus xm to xm, all the values of x between minus xm to xm. So in this case, the total energy is partly kinetic and partly potential. In the intermediate range, we have the energy which is partly kinetic and partly potential. So total energy in this intermediate range will be is equal to kinetic energy plus potential energy. That means half mv square plus half kx square, right? This is half mv square plus half kx square, but in the above case we just find that total energy is equal to half kxm square. So we are going to substitute it here, and if we solve it, we can find that the kinetic energy or half mv square is equal to half k xm square minus x square, right? So we can find the velocity, and it is equal to, velocity square is equal to k upon m xm square minus x square, or v is equal to under root k upon m xm square minus x square. This is the velocity in intermediate range. We can find the velocity for any value of x. Now in the third case, we have the equilibrium position. That means at x is equal to 0. So this is the equilibrium position, and equilibrium position means at x is equal to 0. For that case, the potential energy u, the potential energy u, or we can write it as simply potential energy at x is equal to 0, it is half k x square means 0 square, that means it is 0, and kinetic energy is equal to half m v m square. Now I am writing vm because at equilibrium position the velocity of the spring is maximum, or kinetic energy is maximum, so it is equal to half m vm square. Also it is equal to total energy, because the sum should be total energy, should be equal to total energy. So we can write that total energy is equal to kinetic plus potential. That means half k xm square is equal to half m vm square plus 0, and if we equate these, then we can find this maximum velocity. It is equal to under root k upon m xm. So this is the maximum velocity or maximum speed that spring can achieve. Now we can show this variation on a graph also. We can draw a graph between displacement and energy. Now if we draw a graph between displacement and energy, so the total energy is constant and it is equal to half k xm square. This is energy and this is displacement. So the total energy is equal to half k xm square and is constant throughout the motion. But at extreme positions, the kinetic energy is minimum or zero and potential energy is maximum. So at extreme position, if we draw the curves, so this curve represent potential energy, because at extreme positions plus xm and minus xm, the potential energy is maximum and is equal to half k xm square. And at center or the equilibrium position, this value of potential energy is zero. But in case of kinetic energy, it is zero at extreme positions and maximum and equal to half k xm square at equilibrium position. So this curve represent kinetic energy. This is how we can draw the graph for the conservation of energy in an elastic spring. So total energy is half k xm square, that is fixed. At extreme position, kinetic energy is zero and potential energy is equal to half k xm square. At equilibrium position, potential energy is zero, kinetic energy is half k xm square, and in intermediate range they are partly kinetic, partly positive, and the velocity can be given by the formula under root k upon m under xm square minus x square. So this was all about the elastic spring. That's all for the video. For further videos, stay tuned and keep studying. Thank you.